In the early history of science, electricity and magnetism existed as two distant mysteries, observed in everyday life yet understood only through fragments of explanation. Long before they became central pillars of physics, both phenomena were regarded as curiosities of nature rather than expressions of a unified law. Ancient civilizations encountered them separately and interpreted them through philosophy, myth, and limited experimentation. The attraction of rubbed amber, later known as static electricity, puzzled Greek thinkers, while the strange directional behavior of lodestones guided travelers without revealing its underlying cause. For centuries, these effects lived in separate intellectual worlds, sharing no common explanation and rarely even being mentioned together. The Greeks were among the first to document electrical effects, although their understanding was purely descriptive. Thales of Miletus observed that amber, when rubbed with fur, could attract small bits of straw or feathers. This phenomenon was striking, but seemed isolated, a peculiar trick of matter rather than a universal principle. The Greeks had no concept of electric charge, current, or field. To them, the behavior of amber was an example of hidden qualities within materials, not a force that could shape the structure of the universe. Magnetism, by contrast, appeared more stable and predictable. Lodestones consistently attracted iron, and their behavior did not depend on rubbing or preparation. This consistency led magnetism to be associated with Earth itself, particularly after the discovery that a freely suspended magnet points north and south. During the medieval period, progress in understanding both electricity and magnetism slowed, but their separation as concepts remained intact. Scholars focused more on preserving classical knowledge than on systematic experimentation. Electricity continued to be seen as a minor curiosity, often demonstrated in courtly entertainment or philosophical discussions. Magnetism found more practical use, especially in navigation. The magnetic compass revolutionized travel and trade, yet even as its importance grew, magnetism was still regarded as a unique property of certain stones and metals, not as part of a broader physical framework. There was no compelling reason, at least from observation alone, to suspect a deep relationship between the attraction of amber and the guiding power of a compass. The Renaissance marked a turning point, as experimental science slowly replaced purely philosophical reasoning. William Gilbert, an English physician and natural philosopher, played a crucial role in clarifying the distinction between electricity and magnetism. In his 1600 work De Magnete, Gilbert carefully studied magnetic phenomena and compared them with electrical effects. He introduced the term electricus to describe substances that attract light objects after being rubbed. Importantly, Gilbert argued that electricity and magnetism were fundamentally different. He showed that many materials could exhibit electrical attraction, while magnetism was largely confined to iron and lodestone. He also demonstrated that electric attraction was temporary, while magnetic attraction was more permanent and directional. Rather than unifying the two, Gilbert's careful experiments reinforced the idea that they were separate forces governed by different rules. As scientific instruments improved in the 17th and 18th centuries, electricity began to attract increasing attention. Experiments with glass rods, resin, and metal spheres revealed sparks, shocks, and glowing discharges. The invention of the Leyden jar allowed electricity to be stored, transforming it from a fleeting effect into something that could be accumulated and released at will. These developments gave electricity an almost theatrical presence. Public demonstrations of electrical machines amazed audiences, producing sparks, shocks, and even medical treatments. Magnetism, meanwhile, seemed comparatively quiet and unchanging. Its effects were steady rather than explosive, useful for navigation and simple mechanical devices, but lacking the dramatic flair of electrical experiments. This difference in behavior further strengthened the belief that electricity and magnetism were unrelated. Electricity appeared dynamic, violent, and fleeting, while magnetism seemed calm, persistent, and orderly. Even the language used to describe them emphasized separation. Electricity was spoken of in terms of fluids, charges, and sparks, while magnetism was discussed through poles, attraction, and alignment with Earth. There was no obvious experimental evidence suggesting that one could transform into the other. Scientists classified them as distinct forces, each deserving its own theories and laws. By the 18th century, the study of electricity had advanced significantly through the work of figures like Benjamin Franklin, Charles Augustin de Coulomb, and Alessandro Volta. Franklin's experiments with lightning suggested that electricity was a natural phenomenon on a grand scale, capable of shaping storms and striking the earth itself. Coulomb quantified electrical attraction and repulsion, showing that electric force followed a precise mathematical law. Volta's invention of the electric battery provided a steady source of electric current, opening new avenues for experimentation. Yet even as electricity became more mathematically defined and technologically useful, magnetism remained conceptually separate. Coulomb also studied magnetism and found similar inverse, square laws, but similarity did not imply unity. Many scientists viewed this as coincidence rather than evidence of a deeper connection. At this stage, the separation between electricity and magnetism was not merely a lack of connection. It was an assumption embedded in scientific thinking. The prevailing view was that nature contained multiple fundamental forces, each operating independently. Gravity governed celestial motion, electricity produced sparks and shocks, magnetism guided compasses, and heat flowed from hot objects to cold ones. The idea that these forces might be different expressions of the same underlying reality seemed speculative at best. Without a clear experimental link, there was little motivation to challenge this framework. The early 19th century began to destabilize this comfortable separation. The growing availability of steady electric currents from batteries allowed scientists to explore new experimental configurations. Still, at the dawn of the century, no one expected electricity to have anything to do with magnetism beyond superficial resemblance. When Hans Christian Ørsted discovered in 1820 that an electric current could deflect a magnetic compass needle, the result shocked the scientific community. This was the first clear evidence that electricity and magnetism interacted directly. Yet even this discovery did not immediately unify the two forces in the minds of all scientists. Some interpreted Ørsted's result as a special effect, not a general principle. The old habit of thinking in separate categories was difficult to abandon. Before Ørsted, the intellectual landscape was shaped by centuries of separation. This historical context is essential to understand why later experiments, such as Rowland's rotating disk, were so important. When scientists first encountered evidence linking electricity and magnetism, they were not starting from a blank slate. They were challenging deeply rooted assumptions about how nature was organized. The belief in separation was not irrational. It was supported by generations of observation that showed electricity and magnetism behaving differently in most everyday situations. Even after Ørsted's discovery, many questions remained unanswered. Did electricity always produce magnetism, or only in special circumstances? Was magnetism a separate force influenced by electricity, or was it actually a manifestation of electrical motion? These questions could not even be properly asked without recognizing how firmly the idea of separation had been established. The rotating disk experiment later addressed these questions precisely because scientists had come to see electricity and magnetism as potentially linked, but not yet fully unified. Looking back, the long period during which electricity and magnetism were considered separate reveals something profound about scientific progress. Knowledge does not advance simply by accumulating facts. It advances by changing the way those facts are interpreted. For centuries, people observed electric attraction and magnetic alignment without seeing any reason to connect them. The separation was not due to ignorance or lack of intelligence, but to the limitations of available experiments and conceptual tools. Only when technology, mathematics, and experimental precision reached a certain level did it become possible to challenge the old boundaries. The story of electricity and magnetism as separate forces also highlights the role of expectation in science. Scientists often see what they are prepared to see. As long as electricity and magnetism were expected to be different, experiments were designed and interpreted in ways that reinforced that belief. Once the possibility of connection emerged, new experiments were conceived that could reveal deeper relationships. This shift in perspective transformed isolated curiosities into components of a unified theory. In this sense, the early separation of electricity and magnetism was not a failure, but a necessary stage in understanding. It allowed each phenomenon to be studied carefully on its own terms, leading to precise laws and reliable observations. These foundations later made unification possible. Without Coulomb's law of electric force or careful studies of magnetic poles and fields, the eventual synthesis would have lacked rigor. The very act of separating the phenomena laid the groundwork for recognizing their unity. Thus, the idea that electricity and magnetism were once thought to be entirely separate forces is more than a historical footnote. It is a reminder of how scientific understanding evolves, shaped by culture, technology, and imagination. What appears obvious in hindsight was once deeply counterintuitive. The path from amber and lodestones to electromagnetic fields was long and indirect, marked by centuries of separation before unity emerged. This historical separation sets the stage for understanding why later experiments, especially those proving that moving electric charge creates magnetism, were so revolutionary. They did not merely add new facts, they overturned an ancient division in human thought and revealed a deeper coherence in the natural world. In the latter half of the 19th century, physics stood at a crossroads between classical ideas and a new, more unified understanding of natural forces. Electricity and magnetism were no longer complete strangers, yet their relationship was still not fully understood. Experiments had shown that electric currents could influence magnets, but an essential question lingered beneath the surface of all this progress. Was magnetism caused by something special about currents flowing in wires, or was it simply the result of electric charge in motion, regardless of how that motion occurred? This question was subtle, but answering it would determine whether electricity and magnetism were merely interacting forces or fundamentally the same phenomenon viewed from different angles. Henry Augustus Rowland emerged within this intellectual climate as a physicist willing to challenge assumptions that others accepted quietly. Educated at Rensselaer Polytechnic Institute and later working at Johns Hopkins University, Rowland was deeply influenced by the growing precision of experimental physics in Europe. He believed that theory must always be anchored to careful measurement. At the time, Maxwell's electromagnetic theory had already suggested a deep unity between electric and magnetic effects, but not all physicists were convinced. Many respected scientists still questioned whether magnetism truly arose from moving electric charge or whether it required something more, such as the special structure of a conducting wire or the presence of a closed circuit. The dominant experimental evidence for electromagnetism involved currents flowing through wires. When current passed through a conductor, a magnetic field appeared around it. This fact was well established. However, critics argued that a current was more than just moving charge. It involved chemical processes, interactions with the material of the wire, and complex internal mechanisms. Perhaps magnetism arose from these factors rather than from motion itself. To resolve this debate, an experiment was needed that stripped the phenomenon down to its most essential elements. Rowland's genius lay in recognizing that the purest test would involve electric charge moving through space without being part of a conventional current. The idea of using a rotating charged object was bold. It required imagining electric charge not merely as something that flowed invisibly through wires, but as a physical quantity that could be carried, stored, and mechanically transported. Rowland envisioned a flat disk made of an insulating material that could hold electric charge on its surface. If this disk were spun rapidly, the charge would move in a circular path. There would be motion, but no wire, no battery, and no chemical processes associated with current. If magnetism appeared under these conditions, it would strongly suggest that motion alone was responsible. Designing such an experiment was far from simple. The magnetic effects expected from a rotating charged disk were extremely weak, far weaker than those produced by ordinary currents. Detecting them required instruments of extraordinary sensitivity and a meticulous approach to eliminating sources of error. Rowland understood that even slight vibrations, stray magnetic fields from the Earth, or imperfections in the apparatus could overwhelm the tiny signal he hoped to observe. This was not an experiment that could succeed through dramatic effects. It would succeed only through patience and precision. The disk itself was carefully constructed and coated so that it could be uniformly charged. Maintaining this charge while the disk rotated posed a significant challenge, as electrical leakage could quickly dissipate it. Rowland employed insulating supports and took great care in the materials he used, ensuring that the charge remained stable during rotation. The disk was set spinning at high speed, converting stationary electric charge into moving charge distributed along a circular path. To detect the magnetic field, Rowland used sensitive galvanometers and magnetic needles placed near the rotating disk. These instruments were capable of responding to extremely small magnetic influences. The setup required careful calibration, with control experiments performed to ensure that any observed effects were truly due to the rotating charge and not to mechanical motion, air currents, or static electric forces. Rowland repeated his measurements many times, reversing the direction of rotation and changing the sign of the charge to confirm the consistency of the results. When the disk rotated, the instruments responded. A magnetic effect appeared, aligned precisely with what theory predicted for a loop of moving charge. When the direction of rotation was reversed, the magnetic effect reversed as well. When the disk stopped, the magnetic signal vanished. These patterns were not random or ambiguous. They followed clear, reproducible rules. The conclusion was unavoidable. The motion of electric charge alone was sufficient to produce a magnetic field. This result was remarkable not only for what it showed, but for what it ruled out. It demonstrated that magnetism did not depend on the presence of a conducting wire, nor on the chemical or thermal processes associated with electric currents. The essential ingredient was motion. Electric charge, when set into motion, generated magnetism. This insight cut through decades of uncertainty and speculation, providing a clean experimental answer to a fundamental question. Rowland's work did not exist in isolation. It fit neatly into the broader framework of Maxwell's equations, which treated electric and magnetic fields as interconnected aspects of a single electromagnetic field. Yet Maxwell's theory, for all its mathematical beauty, needed experimental confirmation to gain universal acceptance. Rowland's rotating disk provided exactly that. It served as a bridge between abstract theory and tangible measurement, showing that Maxwell's ideas were not just elegant equations, but accurate descriptions of physical reality. The experiment also highlighted a shift in how physicists thought about forces. Instead of viewing electricity and magnetism as actions at a distance between objects, scientists increasingly began to think in terms of fields filling space. The rotating disk did not directly push or pull on a magnet through contact. It altered the magnetic field in the surrounding space. This field-based perspective would later prove essential for understanding electromagnetic waves, light, and even the structure of space-time itself. Despite its importance, Rowland's experiment did not immediately capture public attention. There were no sparks, no loud discharges, no dramatic visual displays. Its success lay in subtle deflections and careful measurements that only trained physicists could fully appreciate. Yet within the scientific community, its impact was profound. It removed a lingering doubt about the nature of magnetism and reinforced the idea that electric charge and its motion were fundamental. The rotating disk experiment also demonstrated the power of experimental imagination. Rowland did not invent new mathematical theories. Instead, he devised a way to test an existing idea in a novel context. By asking a simple but deep question and designing an experiment that addressed it directly, he advanced physics in a way that theory alone could not. This approach exemplifies the best traditions of experimental science, where creativity and rigor work hand in hand. Over time, the implications of Rowland's findings spread outward. The realization that magnetism arises from moving charge became a cornerstone of electromagnetic theory. It helped scientists understand why electric currents create magnetic fields, why magnetic materials behave as they do, and how electromagnetic radiation propagates through space. Later developments, including Einstein's theory of relativity, would reveal even deeper connections, showing that electric and magnetic fields transform into one another depending on the observer's motion. In this broader context, Rowland's experiment can be seen as an early step toward a relativistic view of electromagnetism. The rotating disk also carried symbolic significance. It showed that mechanical motion and electrical phenomena were not separate domains, but could intersect in fundamental ways. A simple act of rotation, something as old as the wheel, could generate a magnetic field when combined with electric charge. This blending of mechanics and electromagnetism foreshadowed the increasingly unified view of physics that would dominate the 20th century. Rowland's proof of magnetic motion stands as a reminder that progress in science often comes from asking questions that others overlook. The idea that moving charge creates magnetism may seem obvious today, but in Rowland's time it was far from settled. By isolating the essential variables and eliminating alternative explanations, he transformed a theoretical expectation into an experimental fact. In the end, The rotating disk experiment was more than a technical achievement. It was a conceptual milestone that clarified the nature of one of the fundamental forces of nature. It showed that magnetism is not an independent mystery layered on top of electricity, but a natural consequence of electric charge in motion. This realization reshaped the way physicists understood the world, reinforcing the idea that diverse phenomena can arise from simple underlying principles. Through a spinning disk and painstaking measurement, Henry Rowland helped reveal the hidden unity at the heart of physics. The idea that moving electric charge creates a magnetic field is now one of the most fundamental principles in physics, taught early and accepted without hesitation. Yet this clarity is the result of a long struggle to turn suspicion into certainty. For decades, scientists stood at the edge of understanding, aware that electricity and magnetism were connected, but unsure of the precise nature of that connection. The proof that motion of charge itself gives rise to magnetism did not simply add another fact to physics. It resolved a deep conceptual uncertainty about what magnetism truly is. Before this proof emerged, magnetism often appeared as something almost intrinsic to certain materials. Iron magnets seemed to possess an internal power, an invisible property that allowed them to attract or repel. Even when electric currents were shown to influence magnets, it was tempting to believe that the wire, the material, or the chemical processes involved played a decisive role. A current was not seen as merely moving charge. It was seen as a complex phenomenon tied to conductors and batteries. As long as magnetism was observed only in the presence of such systems, doubt remained about its true origin. The crucial shift came when physicists began to think of electric charge as something that could exist independently of wires and circuits. Charge could be stored on surfaces, distributed across objects, and carried through space. Once this perspective took hold, a new and sharper question emerged. If charge is moved mechanically, without any current in the traditional sense, will magnetism still appear? If the answer were yes, then magnetism would be revealed as nothing more and nothing less than a consequence of electric motion. This question was not easy to answer experimentally. The magnetic fields produced by moving charge without a wire are extremely weak, far weaker than those generated by currents in conductors. Nature does not make this test dramatic. Instead, it demands patience, precision, and confidence in subtle signals. The challenge was not only to observe a magnetic effect, but to prove beyond doubt that it came from the motion of charge and not from some hidden current or experimental artifact. The rotating charged disk became the perfect instrument for this purpose. By placing electric charge on an insulating disk and setting it into rotation, physicists created a situation in which charge moved in a clear, controlled path. There was no closed circuit, no flowing electrons inside a metal, and no battery driving the motion. The charge was simply being carried around by mechanical rotation. In essence, this set up isolated motion as the single variable under investigation. When the disk was stationary, the charged surface produced electric effects, but no magnetic influence. Sensitive detectors placed nearby remained still, indicating the absence of magnetism. This alone was important because it confirmed that static charge does not create a magnetic field. Only when motion entered the picture did anything change. As the disk began to rotate, the detectors responded. A magnetic field appeared, faint but unmistakable, aligned in the precise direction predicted by electromagnetic theory. The behavior of this magnetic field followed strict rules. Reversing the direction of rotation reversed the direction of the magnetic field. Changing the amount of charge altered the strength of the field. Stopping the disk caused the magnetic effect to vanish instantly. These patterns were not random, they were systematic and reproducible. They matched the behavior of magnetism generated by conventional electric currents, despite the absence of wires or circuits. This was the decisive proof. It showed that magnetism does not depend on the structure of a conductor, the chemistry of a battery, or the presence of a closed electrical loop. The only essential requirement is motion of electric charge. When charge moves, it alters the surrounding space in a way that we recognize as a magnetic field. When the motion stops, the magnetic field disappears. This insight transformed magnetism from a mysterious property into a logical consequence of electricity. Magnetism was no longer something that certain materials simply possessed. It was an effect produced whenever electric charge was in motion. Iron magnets, currents in wires, and rotating charged objects all fit into the same framework. They differed only in how charge was arranged and how it moved. The proof also strengthened the emerging concept of fields as real physical entities. The rotating disk did not push directly on a magnet through contact or mechanical force. Instead, it changed the conditions of space around it, creating a magnetic field that extended outward and influenced other objects. This field existed even in empty space, independent of matter. Such a view was revolutionary, shifting physics away from the idea of forces acting instantaneously at a distance and toward a vision of space filled with dynamic fields. In this context, the proof that moving charge creates magnetism served as a bridge between experiment and theory. James Clerk, Maxwell's equations had already predicted that electric and magnetic fields are interconnected aspects of a single electromagnetic field. According to this theory, electric fields can give rise to magnetic fields when charges move, and changing magnetic fields can produce electric effects. The rotating disk experiment confirmed this prediction in a direct and tangible way. Without such proof, Maxwell's theory might have remained an elegant but controversial mathematical construction. With it, the theory gained experimental credibility. Physicists could now say with confidence that the equations described real processes occurring in nature. This validation encouraged further exploration and led to the acceptance of electromagnetic waves as a physical reality, ultimately explaining light itself as an electromagnetic phenomenon. The proof also reshaped how scientists understood everyday technologies. Electric motors, for example, rely on the magnetic fields created by moving charges in coils of wire. Generators work by moving conductors through magnetic fields, inducing currents. Once magnetism was understood as a product of moving charge, these devices could be analyzed and improved with greater clarity. Engineering became more predictive, less dependent on trial and error. On a deeper level, the idea that magnetism arises from motion forced physicists to rethink the relationship between electricity, magnetism, and motion itself. Later developments in relativity would show that electric and magnetic fields are not absolute entities, but depend on the observer's state of motion. What appears as a purely electric field in one frame of reference can appear as a combination of electric and magnetic fields in another. This profound insight rests on the simple fact established by experiment: motion matters. The proof that moving charge creates magnetism also clarified why magnetism had seemed so different from electricity in everyday experience. Static electric charges can exist without producing magnetism, while many magnetic phenomena involve steady, persistent fields. The difference lies not in the nature of charge, but in its state of motion. Once this distinction is understood, the apparent separation between electricity and magnetism dissolves. Historically, this realization marked the completion of a long journey. From ancient observations of amber and lodestones to precise 19th century experiments, scientists gradually assembled the pieces of a unified picture. The final step was not discovering a new force, but recognizing that an old force had been misunderstood. Magnetism was not an independent actor on the stage of physics. It was electricity in motion. The elegance of this conclusion lies in its simplicity. Nature did not require an additional fundamental ingredient to produce magnetism. It used the same electric charge, governed by the same laws, behaving differently because it was moving. This economy of explanation is one of the hallmarks of successful scientific theories. It reduces complexity without denying richness, showing how diverse phenomena can arise from a single underlying principle. The proof also serves as a powerful example of how experimental science advances. It was not enough to observe that currents produce magnetism. Scientists had to isolate the essential cause and eliminate alternative explanations. By designing experiments that removed wires, circuits, and materials from the equation, physicists revealed the true source of the effect. This approach demonstrates the importance of asking precise questions and building experiments that answer them directly. Today, the statement that moving electric charge creates a magnetic field is so familiar that it can sound trivial. Yet its acceptance represents a major intellectual achievement. It unified two domains of physics, validated a revolutionary theory, and laid the groundwork for technologies that define modern life. From radio communication to medical imaging, the consequences of this insight are woven into the fabric of society. At its core, the proof revealed a hidden unity in nature. What once appeared as separate and unrelated forces were shown to be different expressions of the same underlying reality. Motion, charge, and field became inseparable concepts, each shaping the others. This unity did not merely simplify physics. It deepened it, opening new paths of inquiry that continue to shape science today. In this way, the proof that moving electric charge creates a magnetic field stands as one of the quiet triumphs of physics. It did not arrive with spectacle or drama, but with careful measurement and clear reasoning. Its impact, however, was profound, reshaping how humanity understands the invisible forces that govern the universe. By the time Henry Rowland carried out his rotating disk experiment, James Clerk Maxwell's electromagnetic theory already existed as a towering intellectual achievement. Maxwell had done something extraordinary. He had taken a collection of experimental laws about electricity and magnetism and woven them into a unified mathematical framework. His equations suggested that electric and magnetic fields were not separate entities, but interconnected aspects of a single electromagnetic field. According to this view, magnetism was not an independent force. It emerged naturally when electric charges moved. Yet, for all its elegance, Maxwell's theory faced a familiar challenge in science. Mathematical beauty alone was not enough. It needed decisive experimental support to silence doubt and secure acceptance. In the 19th century, physics was deeply empirical. Theories earned trust only when experiments confirmed them clearly and repeatedly. Maxwell's equations were revolutionary, but they were also abstract and difficult. Many physicists admired their sophistication while quietly wondering whether they described reality or merely an ingenious mathematical construction. Some accepted them enthusiastically, while others treated them with caution. The idea that magnetism was simply electricity in motion seemed plausible, but plausibility was not proof. Rowland's experiment arrived at precisely this moment of uncertainty, providing a critical piece of evidence that Maxwell's framework desperately needed. Maxwell's theory predicted that any moving electric charge should generate a magnetic field. This prediction was far-reaching. It implied that magnetism was not tied to special materials or mysterious internal properties, but arose whenever charge moved through space. However, most experimental demonstrations of magnetism involved currents flowing through wires. Skeptics could argue that the wire itself, or the complex processes within it, played a role. Maxwell's equations did not depend on wires. They depended on charge and motion. What was missing was a clean experiment that reflected this simplicity. Rowland's rotating disk did exactly that. By taking electric charge out of a conventional circuit and placing it on an insulating disk, he removed the conductor from the equation. When that charged disk rotated, the charge moved, and a magnetic field appeared. This was not an incidental result. It was a direct confirmation of Maxwell's central idea. The experiment translated abstract equations into physical reality. It showed that Maxwell's theory was not merely a convenient description of currents in wires, but a universal law governing electric charge wherever it existed. This confirmation mattered because Maxwell's theory went far beyond explaining magnetism. It predicted the existence of electromagnetic waves, disturbances in electric and magnetic fields that propagate through space at a finite speed. Maxwell calculated that this speed matched the measured speed of light, leading to the astonishing conclusion that light itself is an electromagnetic wave. This claim was radical and, at first, unsettling. If Maxwell's equations were wrong or incomplete, the entire structure would collapse. Experimental confirmation of even one key prediction strengthened confidence in the whole framework. Rowland's work helped legitimize Maxwell's field-based view of nature. Before Maxwell, many physicists preferred mechanical explanations. They imagined forces transmitted through invisible fluids or tiny particles pushing and pulling one another. Maxwell replaced these pictures with fields, continuous entities filling space and evolving according to precise equations. Fields were not directly visible, which made some scientists uncomfortable. Rowland's experiment demonstrated that these fields had measurable effects, even when produced by something as subtle as a rotating charge. The magnetic field predicted by Maxwell was not a mathematical convenience. It was something instruments could detect. The importance of this validation extended into how physicists thought about causality. In Maxwell's theory, electric and magnetic fields influence each other locally in space, rather than acting instantaneously across distances. This was a profound shift from earlier notions of action at a distance. The rotating disk experiment fit naturally into this picture. The moving charge altered the electromagnetic field around it, and that altered field influenced near-by detectors. There was no need to imagine mysterious instantaneous forces leaping across space. Everything happened through the field in accordance with Maxwell's equations. Rowland's results also strengthened the symmetry inherent in Maxwell's theory. The equations treat electricity and magnetism as deeply interconnected, with changing electric fields producing magnetic effects and changing magnetic fields producing electric effects. By showing that magnetism arises directly from electric motion, the rotating disk experiment reinforced this symmetry. It suggested that the separation between electric and magnetic phenomena was a matter of perspective and circumstance, not of fundamental difference. This idea would later become even more powerful with the development of relativity. For Maxwell's contemporaries, the experiment helped resolve lingering doubts. Some physicists had accepted that currents produce magnetism, but hesitated to accept that motion itself was the key factor. Rowland showed that motion was sufficient. This aligned perfectly with Maxwell's mathematical structure, in which current density and charge motion play central roles. The agreement between theory and experiment was not superficial. It was precise and quantitative. The direction and behavior of the magnetic field matched theoretical expectations, leaving little room for alternative interpretations. The broader impact of this confirmation was a shift in scientific confidence. Once Maxwell's equations were seen as reliable, physicists felt justified in using them to explore new phenomena. This confidence led directly to experiments that detected electromagnetic waves, most famously Heinrich Hertz's work in the late 19th century. Hertz's experiments demonstrated that radio waves existed exactly as Maxwell had predicted. Without earlier confirmations like Rowland's, such bold experimental programs might not have been pursued with the same conviction. Rowland's contribution also influenced how physics was taught and communicated. As Maxwell's theory gained acceptance, it became the foundation of electromagnetic education. Students learned to think in terms of fields, charges, and motion rather than isolated forces. The rotating disk experiment served as a powerful conceptual example, illustrating abstract ideas with a concrete physical system. It helped bridge the gap between mathematics and intuition, showing how equations translated into observable effects. In a deeper sense, the experiment underscored a philosophical shift in physics. Maxwell's theory suggested that nature operates according to unified principles, even when phenomena appear different on the surface. Electricity, magnetism, and light were not separate domains, but manifestations of a single underlying structure. Rowland's work supported this unifying vision. By confirming one of Maxwell's key ideas, it encouraged physicists to look for unity elsewhere, paving the way for later syntheses in thermodynamics, quantum theory, and relativity. The validation of Maxwell's theory also had practical consequences. Engineers designing electrical systems increasingly relied on electromagnetic theory rather than empirical rules alone. Understanding that magnetic fields arise from moving charge allowed for more accurate predictions and better designs of motors, generators, and communication systems. Theoretical confidence translated into technological reliability, linking abstract physics to everyday life. With hindsight, it is clear that Maxwell's equations were one of the greatest achievements in science. Yet at the time, their acceptance was not guaranteed. They required champions, experiments, and evidence. Rowland's rotating disk provided precisely the kind of evidence that turned skepticism into trust. It did not prove every aspect of Maxwell's theory, but it confirmed a crucial pillar upon which the rest could stand. This episode illustrates how scientific revolutions often unfold. A bold theory appears, challenging existing categories and habits of thought. At first, it is admired but doubted. Gradually, experiments accumulate that support its predictions, each one strengthening confidence. Eventually, the theory becomes so well established that it feels inevitable. Maxwell's theory followed this path, and Rowland's experiment was one of the stepping stones that made its triumph possible. The importance of the rotating disk experiment, therefore, lies not only in what it showed about magnetism, but in what it did for theoretical physics as a whole. It demonstrated that even the most abstract mathematical ideas can and must be tested against reality. It showed that careful experimentation can illuminate deep principles, and it reinforced the idea that the laws of nature are unified, elegant, and discoverable. In confirming Maxwell's view that magnetism arises from moving electric charge, Rowland helped secure a new way of understanding the physical world. Fields replaced forces acting at a distance, unity replaced fragmentation, and theory and experiment moved into closer alignment. The consequences of this shift continue to shape modern physics, from the technologies we use daily to the deepest theories about space, time, and energy. Through a quietly decisive experiment, the foundations of electromagnetic theory were strengthened, allowing one of the most powerful frameworks in science to take its rightful place at the center of our understanding of nature. The influence of Rowland's rotating disk experiment did not end with settling a theoretical debate in 19th century physics. Its true significance unfolded gradually, spreading outward into technology, education, and the broader way humans understand and use electromagnetic forces. What began as a subtle laboratory demonstration became a cornerstone for modern science and engineering, shaping devices, systems, and ideas that define contemporary life. The experiment's legacy lies not in spectacle, but in the clarity it brought to one of nature's most important principles, that magnetism is a direct consequence of moving electric charge. Once this principle was firmly established, engineers and physicists gained a unified framework for designing electrical machines. Electric motors, which convert electrical energy into mechanical motion, rely on magnetic fields generated by moving charges in coils of wire. Generators, which do the reverse, depend on the motion of conductors through magnetic fields to induce currents. Understanding that magnetism arises from charge motion allowed these devices to be analyzed using a single set of laws rather than a collection of empirical rules. This led to more efficient designs, better control, and greater reliability. Power plants, factories, and transportation systems all benefited from this deeper theoretical foundation. The telecommunications revolution also rests on this insight. Radio waves, microwaves, and other forms of electromagnetic radiation are produced by accelerating electric charges. Antennas work by driving charges back and forth, creating oscillating electric and magnetic fields that propagate through space. Without the clear understanding that moving charge generates magnetic effects and that changing magnetic fields generate electric effects, the development of wireless communication would have been far more difficult. From early radio broadcasts to modern mobile networks and satellite communication, the legacy of electromagnetic theory is ever present. In medicine, the consequences are equally profound. Technologies such as magnetic resonance imaging rely on precise control and understanding of magnetic fields and their interaction with electric currents and charged particles. The ability to predict and manipulate these fields depends on the unified view of electricity and magnetism that experiments like Rowland's helped establish. Even diagnostic tools and therapeutic devices that seem far removed from 19th century physics are grounded in the same principles of moving charge and magnetic response. Beyond specific technologies, the experiment reshaped scientific education. Physics curricula began to emphasize fields and motion rather than isolated forces. Students learned that magnetism is not an independent mystery, but a natural outcome of electric behavior. This perspective fosters a more coherent understanding of physical laws, making it easier to grasp advanced topics such as electromagnetic waves, relativity, and quantum electrodynamics. The rotating disk experiment often appears in discussions as a conceptual milestone, illustrating how careful experimentation can reveal deep connections between seemingly different phenomena. The broader scientific world, you also changed. By demonstrating that magnetism emerges from motion, the experiment contributed to a growing appreciation of symmetry and unity in nature. Laws that once appeared fragmented were now seen as interconnected expressions of deeper principles. This mindset encouraged physicists to search for unification in other areas, such as the relationship between space and time or the connection between energy and mass. The success of electromagnetic unification served as an inspiring example, suggesting that nature favors elegant, unified descriptions. Later developments in physics built directly on this foundation. Einstein's theory of special relativity revealed that electric and magnetic fields are not absolute, but depend on the observer's motion. A purely electric field in one frame of reference can appear as a combination of electric and magnetic fields in another. This profound result relies on the established fact that magnetism is tied to motion. Without experimental confirmation that moving charge produces magnetism, such a reinterpretation would have lacked credibility. Rowland's experiment thus played a quiet but essential role in preparing the ground for one of the greatest revolutions in physics. In the 20th century, quantum theory further deepened the story. At the quantum level, charged particles such as electrons carry intrinsic properties that give rise to magnetic moments. These behaviors are still described using the same electromagnetic principles, now expressed in more sophisticated mathematical language. The classical insight that motion of charge produces magnetic effects remains valid, serving as the macroscopic limit of more complex quantum phenomena. The continuity between classical and quantum descriptions highlights the enduring relevance of the original experimental proof. The experiment's influence can also be seen in how scientists approach research. Rowland's work exemplified a careful balance between theory and experiment. He did not reject existing ideas, nor did he accept them uncritically. Instead, he designed an experiment that isolated a key assumption and tested it directly. This methodology became a model for future investigations. When new theories arise, physicists often seek similarly clean and decisive experiments to probe their foundations. The rotating disk stands as an early example of this disciplined approach. On a cultural level, the unification of electricity and magnetism changed how society perceived science. It demonstrated that invisible forces governing everyday technologies follow precise, discoverable laws. This realization contributed to public confidence in scientific progress and technological innovation. As electric power spread through cities and communication networks spanned continents, the underlying electromagnetic principles became symbols of modernity and human ingenuity. The quiet laboratory work of figures like Rowland ultimately supported sweeping social transformations. The long-term impact of this experiment also includes its role in shaping scientific language. Terms such as field, current density, and electromagnetic interaction became central concepts. They provided a common vocabulary for physicists, engineers, and educators. This shared language made collaboration and knowledge transfer more efficient, accelerating progress across disciplines. The clarity gained from understanding magnetism as a consequence of motion simplified communication and reduced confusion that had persisted for centuries. From a philosophical perspective, the experiment reinforced a key lesson about nature. Complexity often arises from simple rules. Magnetism, once thought to be a distinct and perhaps mysterious force, emerged from the straightforward idea of moving charge. This reduction did not diminish the richness of magnetic phenomena. Instead, it made them more comprehensible. Such insights encourage humility and curiosity, reminding scientists that even familiar phenomena may have deeper explanations waiting to be uncovered. In the modern world, where electromagnetic effects underpin everything from computing to renewable energy, it is easy to take this understanding for granted. Yet every electric motor, transformer, wireless device, and imaging system traces its conceptual lineage back to the realization that motion of charge creates magnetism. The rotating disk experiment stands as one of the key moments when this realization became undeniable. The true power of Rowland's contribution lies in its endurance. Scientific theories evolve, technologies advance, and instruments become more sophisticated, but the core principle demonstrated by the rotating disk remains unchanged. It continues to be taught, applied, and extended, forming part of the stable foundation upon which new discoveries are built. Few experiments achieve such lasting influence. In reflecting on this legacy, one sees that the experiment's importance is not confined to a single era or discipline. It connects 19th century laboratory physics with 21st century technology, linking abstract theory to practical application. It exemplifies how careful reasoning and precise measurement can reveal truths that reshape both science and society. Ultimately, the rotating disk that once spun quietly in a laboratory helped set in motion a cascade of understanding that still shapes the modern world. By proving that magnetism arises from moving electric charge, it unified concepts, empowered technology, and deepened humanity's grasp of the natural order. Its impact is woven into the fabric of contemporary life, a testament to how even the most subtle experiments can change the course of physics and, through it, the course of history.